example, we have these two rods like a ladder which are pin jointed over here, so they can move like this. And from here, from this pin, a mass M is hanging. For convenience, we have taken these two rods as massless. This and this, they are massless. Both of them, they have a length L. And here is a string which is tied from the center of these, and the length of this is L by 2. And from here, mass M is hanging. All the surfaces, they are frictionless. If the string is cut, then obviously it will fall down. So this tension is keeping it in this configuration. We are asked, what is the tension in the string? If this is L, and this is central point, and this is L by 2, this is middle of this is middle of this, you join it. So this line is half of this. So it means, that is, if this is L by 2, so this is also L, that is, angle is given as 60 degree. All the angles, that is equilateral angle, so this is also 60 degree. If we draw the force diagram of this, and we know that is all the surfaces are frictionless, and if we take this whole body as one body, so what we observe is, that is, this is over here, this is over here. If normal reaction is over here, so similarly normal reaction will be over here. So this whole structure is supported on these two by these two normal reactions. So we can say 2N is equal to mg. Obviously rest all the internal forces. Even the tension is internal forces, we are taking the whole body as one body. So normal reaction this is supporting the whole structure, that is m into g, it is supporting it. These two rods, they are massless. So 2N is equal to mg, so N comes out to be mg by 2. We have found the normal reaction. Now what we do is, that is, we have a confusion over here. So now we don't know, that is, what is happening over here. So let's take the torques about O, and let's take this as element. We have taken this as element. What does it mean? It means, that is, now we are taking this point as O. Over here we have a normal reaction. So over here we have a normal reaction is equal to mg by 2. That is, we can say directly write as mg by 2 is the force over here. And this way it is the tension. We have a lots of confusion over here, that what are the forces acting over here. So wherever there is a confusion, take the torques about that axis, because now the torque of all the forces, what sort of forces they are acting over here, their torque about this axis is going to be equal to 0, because as we know, torque is force into perpendicular distance between line of force and axis rotation. All that forces, they shall be passing through this axis only, so their distance is equal to 0 from the axis rotation, so that's why their torque is equal to 0. That's why we are considering torque about O. So now about this torque about O is obviously net torque about O is equal to 0, because this rod is neither rotating in the clockwise direction nor in the anti-clockwise direction. So if you take this as rod, it is hinged over here. If you apply force like this, this tries to rotate this way, that is anti-clockwise, and this tries to rotate it in the clockwise direction. This rod is in translational as well as rotational equilibrium. There is no rotation either in clockwise direction or in anti-clockwise direction. So clockwise movements is equal to anti-clockwise movements, because the net torque has to be equal to 0. So now let's see what are the torques like. Torque of mg about O, that is mg, this is force, this is line of force, this is acceleration, so we are interested in this distance. And if this is L, we know this is 60 degree. If this is L, so this is L cos 60 degree, and this is L sin 60 degree. So this is force. So this is force, this is line of force, this is acceleration. We have to find this. That is, either we say this or this same thing. So this is 60 degree. So this was L. So this is L cos 60. So this is L cos 60. So torque of mg by 2 along this axis is mg by 2 into L cos 60, and that should be equal to, that is, the anti-clockwise movements of this T, that is T into, now this is line of force, acceleration is here, so we are interested in finding what is this distance. So this is L by 2, this is 60 degree, so this is L by 2, this is L by 2 cos 60, and this is L by 2 sin 60. So this is L by 2 sin 60 degree, and from here we can just put the values and we can get the answer. Now let's move one step ahead, and let's consider these two rods as not as massless but having some mass. Or let's say these two rods, they are of different masses. Then how we can proceed about it? So if we draw the diagram, and let's say these two rods, they have masses m1 and m2. we can take it. But this mass is uniformly distributed. Otherwise, we will to find the center of mass of these two rods, and we may have to use the integration process. So now let's simplify it, and we are going just one step ahead of the previous question, and we are taking the masses as m1 and m2, and the mass distribution is uniform of these two rods. That is, these two rods, they have a uniform linear mass density. So it means that is m1g is acting over here at its center, and its weight is acting at its center, m2g. Same way, normal reaction now, it will be different. N1 will be here and N2 will be here. Both the rods, they have a length L. Once again, the angle is 60 degree. Let's take it as 60 degree, or let's take it as theta. Any angle, let's take it as theta only. Why take 60 degree only? Let's take this angle as theta. Now, because this whole structure is neither moving in the upward direction nor moving in the downward direction, it means summation of forces along y-axis is equal to 0. It means the upward forces, that is N1 plus N2, is equal to mg plus m1g plus m2g. Net force along the y-axis is equal to 0. We have used that. So we have made one equation. Now let's, as we had done earlier, we can take this element. Let's take this element, right? If we take this element, so diagram is something like this. So now we take the moments or torques about this point O. Torque about O, net torque about O is equal to 0. So if we see over here, that is this force, N1 is trying to move it this way, mg is trying to move in the anti-clockwise direction, and T is also trying to move it in the anti-clockwise direction. It is only N1 which is trying to move it in the clockwise direction. And eventually this is not rotating, this is in translational equilibrium as well as in the rotational equilibrium. So anti-clockwise movements is equal to clockwise movements because the net torque is equal to 0. Net torque about all the axes is equal to 0. Had there been even net torque about this axis, this axis, this axis, any axis, had there been any net torque, this would have rotated, this would have some alpha about that axis. It is not having any angular acceleration about any axis, so this is in rotational equilibrium. We are considering this element. So now let's take the torques. So it is N1 into this line of force, this distance. That is from here to here. This is L. So this is L cos theta. N1 into this distance. This distance is what? L cos theta. So N1 into L cos theta. It is, what is this? This is clockwise torques. So this is making clockwise torque, and this they are contributing towards the anti-clockwise movements, that is anti-clockwise torque. Both of them, they are trying to rotate it this way. So it is T1, this is line of force, this is acceleration, we have to have this distance, that is, this is L by 2, this is theta, this is L by 2, total length is L, this is in the middle, so this is L by 2, so this is L by 2 cos theta, so this is L by 2 sin theta. So T1 into L by 2 sin theta plus, now of this mg, plus m1g force into perpendicular distance between line of force and acceleration, that this is line of force of m1g. So this is L by 2, this is L by 2 cos theta, so this is also L by 2 cos theta. So into L by 2 cos theta. We get this equation. That is, if we write once again over here, so this comes out to be N1 L cos theta is equal to T1 into L by 2 sin theta plus M1G into L by 2 cos theta. So we have one equation over here, we have second equation over here. We can make more equation. Let's say one more equation, that is, we can take now this element, we can take it. If we consider this element, so it is going to be O. Once again, we can take the moments about this only. So over here it is M2G, and over here is T, and over here is N2, right? Net torque about O is equal to 0. So that's why once again clockwise movements equal to anti-clockwise movements. So if we see, that is, this N2 will try to rotate it in this direction. Which direction? This is anti-clockwise direction. T will try to, if I hold it from here, let's say this is pin jointed over here, if I hold it like this, as if a nail has been inserted into this, now if you apply a force T in this direction, it rotates in this direction, that is in the clockwise movements. So when you apply M2G, it once again rotates in the clockwise direction. So contribution of T and M2G forces, this is towards the clockwise movements, and N2 is contributing towards the anti-clockwise movements. So equation for this, net torque about O is equal to 0 for this thing. So it is going to be N2, N2 is here, this is N2, this line of force, and this distance, this is L. So this is theta, so this is L cos theta. So N2 into L cos theta is, now we have two forces, one is M2G, the other is T, which are trying to rotate it this way. So M2G, torque of M2G is M2G force into perpendicular distance between line of force and axial rotation. This is force, line of force, this is L by 2, so this is L by 2 cos theta. So if this is L by 2 cos theta, so this is also L by 2 cos theta. From here to here is L by 2 cos theta. So this is L by 2 cos theta plus T. T is this way. So we wish to know this. T is in this direction. We need to know what is this. This is L by 2. This is L by 2 cos theta. So this is L by 2 sin theta. T into L by 2 sin theta. So this is equation number 3. So we have 3 equations. From this we can find the value, whatsoever value is being asked.